Hello, so this is a revision video for NCERT Class 12, 2.1 Electrochemical Cells. This is a revision video, so we're only going to cover the essential information you need to know for revision. For deeper explanations and for full video lessons, please check the links in the description below and visit chemistrystudent.com. Electrochemical cells use redox reactions to either produce electricity or use electricity to drive chemical changes. They are essential for understanding how chemical energy is converted into electrical energy through the movement of electrons and ions. There are two main types of electrochemical cells: Voltaic or Galvanic cells that generate electricity from a spontaneous redox reaction, and electrolytic cells that use electricity to force a non-spontaneous redox reaction to occur. All electrochemical cells contain two solid electrodes placed into a liquid called an electrolyte. The anode is the electrode where oxidation always happens, and the cathode is the electrode where reduction always happens. Remember, oxidation equals loss of electrons, reduction equals gain of electrons. Exam tip here, always remember anode as oxidation and cathode as reduction rather than the charges of the electrodes, because the charges of electrodes are different depending on the type of cell. Voltaic or galvanic cells produce electrical energy from a redox reaction that happens without any external energy input. A spontaneous chemical reaction, remember, as having a Gibbs free energy change of less than 0. Electrons flow through an external wire from the anode to the cathode. The anode, where oxidation occurs, is negatively charged, and the cathode, where reduction occurs, is positively charged. Now we've looked at the basics, let's look at galvanic and voltaic cells in a little bit more detail. A simple voltaic cell can be constructed using two half cells connected by a salt bridge and an external wire. A simple half cell consists of a metal electrode, a solid metal, and an electrolyte, a solution containing ions of that metal. A redox equilibrium is established between the solid metal and its ions. This sets up a potential difference between the solid metal and the solution. The position of equilibrium, and hence the total charge or potential of the solid metal electrode, depends on how readily the metal loses or gains electrons. The electrode potential of a half cell cannot be measured directly, but we can compare it to a standard reference, like the standard hydrogen electrode, to determine its relative value. When you take two different half cells, one of the electrodes will have a greater negative potential than the other. This means if you connect them together with a wire, electrons will flow from the anode, where oxidation is going to be happening, to the cathode, where reduction is going to be happening. A salt bridge is required to allow ions to be exchanged freely between half cells, and it prevents a charge buildup. Cations in the salt bridge move towards the cathode half cell, and ions in the salt bridge move towards the anode half. It is really important that ions in the salt bridge aren't reactive. This means when the ions enter each half cell, they don't interfere with the redox processes that occur. All they do is simply carry and balance charge. So let's have a look at that zinc and copper voltaic cell again in a bit more detail. At the anode, the zinc metal is oxidized. The released electrons travel through the external circuit to the cathode, where the copper ions get reduced. Copper 2 plus 2e minus goes to solid copper. As the reaction proceeds, zinc metal is gradually consumed and used up in the anode, and solid copper builds up on the cathode. The electron flow from the anode to the cathode will continue as long as zinc is available to be oxidized and copper ions remain to be reduced. The salt bridge maintains charge balance by allowing ions to move between the two half cells. This prevents charge buildup, which would otherwise stop the redox reactions from occurring. In electrochemistry, cells are written using a shorthand notation. A single vertical line separates different phases, solid, liquid, and aqueous, and a double line represents the salt bridge, separating the two half cells. The anode oxidation half cell is written on the left, and the cathode reduction half cell is written on the right. For example, the zinc and copper electrochemical cell we've just looked at would be represented as Zn solid, straight line, Zn2 plus aqueous, double line, Cu2 plus aqueous, line, Cu solid. This shows us that electrons are flowing from the zinc on the left, the anode, to copper on the right, the cathode, separated by a salt bridge. Electrolytic cells use electrical energy to drive a chemical change for a non-spontaneous reaction, where Gibbs free energy change is greater than zero. Electrons still flow from anode to cathode, but the energy is supplied externally. So now the anode where oxidation occurs is positively charged, and the cathode where reduction occurs is negatively charged. The anode often loses mass because it gets oxidized, and the cathode often gains mass because ions get reduced and stick to its surface. For example, in the electrolysis of molten sodium chloride, chloride ions will be attracted to the positively charged anode and get oxidized into chlorine gas. And at the negatively charged cathode, positively charged sodium ions will be reduced and get turned into sodium. An electrolytic cell is made up of two electrodes placed into an electrolyte and connected to a DC power supply. DC power is really important. AC power doesn't work for electrolysis. An electric current is passed through a liquid or molten ionic substance, the electrolyte, which contains free ions that can move and carry charge. Electrons flow from the DC power supply to the cathode. Positively charged ions migrate to the cathode and gain electrons, they get reduced, whilst negatively charged ions move to the anode and lose electrons, get oxidized, which return to the positive terminal of the power supply. Exam tip here, I'm going to repeat what I said earlier. Always remember the cathode is where reduction takes place and the anode is where oxidation takes place. Here in an electrolytic cell, the cathode is the negatively charged electrode and the anode is the positively charged electrode, which is the opposite way round for a Voltaic cell. But still, the cathode is where reduction happens and the anode is where oxidation happens. If you remember cathode is reduction and anode is oxidation, you will always be correct, regardless of whether a question is referring to electrolysis or Voltaic cells. We can predict the products formed at each electrode based on the type of electrolyte being used. For molten electrolytes, it's quite simple because the only ions we have present are from the ionic compound, so the cation gets reduced at the cathode and the anion is oxidized at the anode. For example, molten sodium chloride, as we saw earlier, would give chlorine at the anode and sodium at the cathode. For aqueous electrolytes, however, things are a little bit different, because water molecules, H2O, naturally ionize and split apart into hydroxide ions and H+ ions. As a result, these ions in the water may compete with the ions from the ionic compound at the anode and cathode for oxidation and reduction. We can use standard electropotential values or reactivity trends to predict which species will get discharged and oxidized or reduced. As a general rule, at the cathode, hydrogen ions get reduced to hydrogen gas if the metal in the ionic compound is more reactive than hydrogen. If, however, the metal in the ionic compound is less reactive than hydrogen, then metal ions from the ionic compound will be reduced and metal gets formed. At the anode, generally hydroxide OH- ions get oxidized to form oxygen gas. However, if halide ions, for example chloride or bromide ions, are present, they will usually be oxidized instead, unless their concentrations are very low. For example, if we now look at the electrolysis of aqueous sodium chloride, the reaction at the anode remains the same because chloride ions will be oxidized instead of hydroxide ions from the water, but at the cathode, hydrogen ions will get reduced instead of sodium ions because sodium is more reactive than hydrogen.